In this video, we present a control architecture for visual navigation for an UAV in the presence of uncertainties. We consider the scenario where a quadrotor UAV takes off from a base robot and detects and lands on a target robot, localizing only using the visual features on the base and target. A visual locking constraint is used in the ascending phase, and a switching parameterizable descending constraint is used in the approaching and landing phases. A fan is used to create wind disturbance. Aruco markers are placed on the base and target to localize the UAV. The UAV is commanded to move horizontally towards the target. However, the controller pushes the UAV upward whenever the origin of the base reaches the VCBF boundary. The controller switches to the approaching phase when the target is detected. The parameters of the DCBF is calculated using the relative position of the UAV in the target frame and the chosen altitude of the focus region. The UAV settles in the focus region to align with the target. The target is equipped with a landing platform to further validate the landing precision enforced by the controller. The controller switches to the landing phase when the UAV is inside the focus region A and the yaw is aligned. The CBF parameters are modified using the chosen landing region B and the position of the UAV. Even in the presence of disturbance, the UAV performs landing successfully. A visualization of the poses and the CBFs is presented to provide a perspective of the experiment. The ground truth GT is obtained from the motion capture system, and it is not used for the pose estimation or anything else in the entire algorithm. The UAV's pose is estimated using the Aruco markers, and it is represented as EST. In the visualization, the blue sphere shows the focus region A, and the small yellow sphere shows the landing region B. The CBF's boundary will be shown with an array of red markers. Since the target is detected at an altitude below K3, K2 becomes 0, and the DCBF boundary becomes a horizontal plane at an altitude of 1.75 meters. The controller forces the UAV to remain above this plane in the approaching phase, even in the presence of uncertainties in the form of disturbance and estimation noise. Though the UAV momentarily violates the constraints due to the introduced uncertainties, the implicit robustness of the CBF enforces the UAV to asymptotically converge to the safe region. The landing CBF ensures the vertical descent of the UAV for a safe and precise landing. An additional perspective of the experiment is provided using the video on the left side. Similar to the previous case, the CBF and adaptive control layers bring the UAV to the safe zone even when it momentarily breaches the constraints due to the uncertainties. Even in this case, K2 becomes 0 as the target is detected at an altitude below K3. Hence, the DCBF boundary becomes a flat plane in the approaching phase. When the controller switches to the landing phase, the DCBF is modified with the parameters obtained from the altitude of the landing region B and the relative position of the UAV at the time of switching. This ensures the vertical descent of the UAV in the landing phase.